Good morning students, let us today conduct the experiment of lag lead compensator network. So the name as it indicates, lag lead compensator network. That means for certain range of frequencies the output lags the input by some angle, and for other range of frequencies the output leads the input by some angle. That's how the name has come to this circuit as lag lead compensator circuit or compensator network. So this is the circuit diagram of the lag lead compensator network. In this circuit diagram we have four components, two resistors and two capacitors, right? R1 and C1 are connected in parallel, R2 and C2 are connected in series, and that is next, this is how they are connected. Okay, so this is the junction of R1 and C1 that is connected to the series combination of R2 and C2. Output is taken from this end, other end of the junction of R1 and C1, and other end of the capacitor. Okay, that is the input where it is connected, that is one end of the junction of R1 C1 and another end of C2, and the output is taken across the series combination of R2 and C2, V0, right? So what we are conducting here students, so it is nothing but we are trying to find the frequency response characteristics of a given lag lead compensator network. That is, we will be plotting the graph of the output voltage in dB or output gain in dB versus frequency, and that is our magnitude response, right, or voltage response. Then frequency response will be to plot the graph of the output, that is phase response will be to plot the graph of the output phase whatever we have obtained versus frequency, right? So these will be the two responses that we are going to plot here. Okay, so this is about the circuit. Then this is the nature of the graph, how we will be getting here. So as it is a lag lead compensating network, so initially as we start the experiment, for the starting frequencies, initial frequencies, the output will lag the input. So this is how we are getting here. This portion from here to here is the lag portion, right? Then from certain frequencies, the next frequencies, right, the output will lead the input. Output will lead the input. So this is how we are getting here, right? Next is the phase response. So phase response also similar thing. So for the initial frequencies, the output is, this portion is showing the lag portion of the output versus input. Then the remaining portion here from this part to this portion is showing the lead portion. We will be getting in the positive side. Okay, this is about the nature of the graph. Students, we are into the conduction of the lag lead compensator network. So as you can see here, I connected the signal generator, right, to the input of the CRO. So where you are able to see the signal here, this is the input signal what you are seeing. This I have maintained it at 2 volts peak to peak. So this is 1 plus 1, 2 volts, 2 into 1. So it is 2 volts peak to peak. So for this frequency of 80 Hz, right, you have to note down the output voltage, then phase angle we have to calculate, and output in dB. Okay. So now let us note down the output voltage. Before that, let us keep it in dual mode and see what is the nature of the, that is input and output we are getting. Okay, so first adjust the X shift here, so that is exactly at the center, then keep it in dual mode. So you can see here, so when I keep it in dual mode, alright, so the output is lagging, the smaller one is the output, so output is lagging the input is starting ahead of the output, or output is starting late from that of the input. So it is, output is lagging the input by some angle. Okay, that is at 80 Hz frequency. So for this frequency, now let us note down the output voltage. Second channel is the output voltage, so adjust it. So here it is, how much, ground it, check for the ground line, so it is X shift. Okay, right, then now keep it in, release the ground switch, adjust it. So it is, X shift is around 0.4, can say 0.4, and below portion, below the ground line, it is 0.4, so it is 0.8. So for a frequency of 80 Hz, output we are getting 0.8 volts peak to peak, 0.8 volt peak to peak. Then next we will note down B and A to calculate the phase angle. Okay. So keep it in XY mode, adjust the X position. Exactly at the center. So now this is approximately 1, this is 1, so it is approximately 2, right? So larger one is A, that is 2, so A is 2. Then what about B? B is 0.4, okay, 0.2 above, 0.2 below, so 0.4 by 2. Okay, so here A is 2, then B is 0.4, right? This is our first reading. Now let us take it for 160 Hz, next set of readings. So around 160 Hz here, you can see 160 Hz I have maintained. So at around 160 Hz, okay. So how we will get the input and the output waveforms? Keep it in dual mode, right? So you can see both are starting from the same point. Both are starting from the same point. That means they are overlapping. Even though their magnitudes are different, but they are starting from the same point. That means both are in phase, right? So what will be the phase angle difference between the two? It is how much? Yes, come on, tell us. So it is 0 degrees, okay, because the phase angle difference between output and input is 0. So you will get here 0 degrees, okay. So this is how we are getting here. So for this portion, now let us next note down the output voltage, okay. So it is in second channel. So this is now we are noting down for 160 Hz, okay. So it has decreased, it is 0.3 below and 0.3 above, okay. So 0.6, okay. So it is 0.6 volts peak to peak. What about B and A? Let us check B and A, that is XY position, XY. So keep it to exactly center position. So we can note here, this is 1 plus 1, 2, B is 2, right? B is sin inverse of B by A, sorry, A is 2, B is 0, so it is coinciding exactly at the origin. So we have B is sin inverse of, it is B by A, okay. So A is 2, B is 0, okay. Now let us next note down the readings for 280 Hz, that is above this. So here students, so we just now observed that below 160 Hz, that is when we took for 80 Hz, the output was lagging the input. Exactly at 160 Hz both are in phase. Then about 160 Hz, that is at 280 Hz, let us observe how will be the output and input waveforms. Next I will adjust it to 280 Hz, that is the input frequency. Okay, so it is around 280 Hz. So for 280 Hz, let us observe the output and input waveforms first. Keep it in dual mode, right? So now you can see here, you can observe here the smaller portion is output. Output is starting ahead of input. You can see here, yeah, output is starting ahead of the input. That means output is leading the input. So above the 160 Hz frequency, output is leading the input. Let us note down the output voltage and the B and A readings. So to observe, note down the output voltage, keep it in channel 2 position. So it is how much? 0.2, 0.4 above. And what about below position? Let us check the ground line, it is correct. So it is 0.4 above. Then what about below the ground axis? That is also 0.4. So it is 0.8. Okay. So 0.8 volts peak to peak. What about B and A readings? Keep it in XY mode. Check for the ground position. Bring it to exactly at the center. X position. Shift it. Then release the ground switch. So it is 1 plus 1, 2. Okay. That is 1 plus 1, 2 we are getting. That is A is 2. How much is B? Right. So it is 0.2 here. This is 0.2. Okay, this is point where it is cutting is a 0.1. It is actually 0.1 plus 0.2, 0.3. Okay, so it is, this is 0.3 and this we are getting 2. Okay, so this is how we are taking the readings. So here we have considered the R1 and R2 values of the circuit as 10 kilo ohms and C1 and C2 as 0.1 microfarad. Just make a note of this. Then the readings whatever we have taken, we'll do the calculation part of those readings. So first for 80 Hz, right, let us calculate the sine. So phase angle, so shift sine inverse of B by A, it is 2 divided by 0.4 divided by 2, 0.4 divided by 2. this comes out to 11.5369 degrees. This is 11.5369 degrees. Similarly, calculate the output in dB, 20 log V0 by Vin. V0 is 0.8 volts peak to peak. So 20 log of V0 is 0.8, this divided by 2. So this comes out to minus 7.9588, minus 7.9588 in dB. So this is clear, that is sin inverse of 0 by 2 is 0, right? It is 0 degrees. Then 20 log that is 0.6 divided by 2, 0.6 divided by 2. So this comes out to minus 10.4575, minus 10.4575 in dB. Similarly, for the third reading, that is for 280 Hz, so it is shift sin inverse of 0.3 divided by 2. So this will be equal to 8.6269, 8.6269 degrees. So you can see here for 80 Hz it is 11.53. From this angle it is lagging, so it has decreased to 0 degrees. From 0 degrees onwards we are getting a positive side, that is 8.6269. It is leading. Okay. So this is the reference position. Below this it is from higher value to 0 degrees it will decrease. Then from this reference value 0 degrees it will increase from 0 degrees to whatever is the higher value. Okay. And similarly next we will find the 20 log V0 by Vn, that is 0.8. So it is same 0.8 divided by 2 whatever we have calculated. So we will get the same, that is minus 7.9588, the same value that you have calculated for the first value. Okay, 0.8 volt divided by 2 volts. So 0.8 by 2 it is the same value, it is minus 7.9588. Okay students, so this is how we are getting the values. That is calculation part. Then this is the waveform that we showed at the beginning. So this is our reference line. So from this reference line, so initially it is in lag position. So from higher value it decreases to 0, right? So then from once it decreases to 0 here, from this portion, so from 0 line again it is increasing in the above direction, right? So this is our reference position, that is 0 line. Below this it is higher value in the negative side, then it decreases to 0, and above this it is in the positive side. From 0 degrees it increases to the positive side in the upper side. Okay. So from the reference position below it is lag, and from the reference position above it is lead, right? So this is how we have conducted the experiment, students, of the RC lag lead compensating network. If there are any queries in this circuit in the conduction part, send your queries to us so that we will clarify your queries. Thank you.